agree that the ball actually has kind of a velocity that's both in the x direction and the y direction. So if I was to just kind of sketch on here, I would probably say that there's a portion of the momentum that's this direction and a portion of the momentum that is this direction. I'd say that this is the momentum in the x direction, and this is the momentum in the y direction. Is that okay so far? All right. Over here, would you agree that this ball also has a momentum in the y direction after it contacts the wall? But it also has a momentum in the x direction after it contacts the wall? So momentum in the x direction and momentum in the y direction. Zooming out on this again, did both momentums change due to the contact with the wall? You can find out. You can figure out the size of each of those momentums. You know that the actual momentum, or the total momentum, is 10 kilograms meters per second. All of you calculated that a few minutes ago. But there's a portion in this direction and a portion in that direction. I'm thinking you've got your 45 degrees there. That must mean it's 45 degrees here as well. You guys remember your trig. Figure out how much of the momentum is in each direction. Do that for both. There's a little symmetry here, so it shouldn't be all that hard for you to figure out. That's why I chose 45 degrees. So take a moment, try it, see what you get. I'm a little unconvinced. Can we kind of agree that the horizontal one's probably based on the cosine of 45? So 10 cosine 45 should give me how much of it's in the horizontal direction? 7.07 kilograms meters per second. The other one's got to be 7.07 as well. It's 45 degrees. Two legs of the triangle have to be the same. In fact, I'm pretty sure that the other recoiling portion here, being that the velocity didn't change, just the direction did. This is 10 kilograms meters per second. So this also must be 7.07. And this one must also be 7.07. It seems to me that the y direction didn't have a change in momentum. All right, it's 7.07 both before and after it strikes the wall. So in this collision, the change in the y momentum, 0. Final minus initial. On the other hand, there is a change in the x direction. Because although the ball is traveling to the right before the collision, it's traveling to the left after the collision. So we probably should pick a direction that we call positive. I've already kind of indicated that up is positive, so how about we make to the right positive? If I do that, the change in momentum in the x direction, well, let's see. That's final minus initial. We're talking about just the x direction right now. So the final momentum in the x direction was negative 7.07 minus the initial momentum, which was positive 7.07. Looks like the total change in momentum, negative 14.07. I'm sorry, 14.14 kilograms meters per second. Now, it's just a change in momentum. Momentum's a vector quantity, just like force is a vector quantity. It's in your best interest to treat it the same way we treated forces, which means pick a direction for X and Y and break your momentum up into an X direction and a Y direction. Yes, ma'am? Here? The mass of the ball was 2, and the velocity was 5 meters per second. So trying to make this smaller so I get a little space. So our definition of momentum is just mass times velocity. So before I found the X portion and the Y portion, I just took the mass 2 and multiplied by 5 to get 10 kilograms meters per second.
So you didn't have to do the minus the 2 times?
Not just to find the momentum of the ball before it hit the wall, no. I did that here to find the change in momentum after it contacted the wall. Does that make sense?
Yeah.
Okay. Now from here, you can figure out the force on the ball. And I hope that that part wasn't hard. You had the time. The same thing we did yesterday. So it just becomes force times time equals change in momentum. In this case, there's the force in the X direction. And we could probably extrapolate that and talk about the force in the Y direction. But it doesn't look like there was a force in the Y direction because there was no change in momentum in the Y direction. There's only a change in momentum in the X direction. That suggests that when the ball struck the wall, the force from the wall was just this way. Not changing its vertical motion, but changing its horizontal motion. Judging by the looks on people's faces, you need more practice. Yep.
Can you get a question that we're finding what would you write then as a final answer? Like the force or the changing?
Depends what the question was. In this question, I think it's appropriate that we asked for change of momentum as one of the answers. I'm sure I would have asked it in parts. And that would have been the answer for the impulse. It would have been negative 14 kilogram meters per second, or 14 kilogram meters per second to the left. That would have been what I'd be looking for. And then I'd probably have a follow-up question where I asked how much force was applied to it, and that's where you would use the time. Is that all right? Let's try. I don't want to change it too much, but I think I need to make sure you guys are getting this idea of 2 dimensions down. So I think we'll look at another 2-dimensional example just to see if it sinks in a little bit. I don't want to make it all about that because it's really not that big a deal. But let's so let's say that I'm trying to find a way to do this so it's not terrible. 4 kilograms and 10 meters per second. And this angle is, let's go with 60 degrees. And after it recoils off the wall, bounce it off at 60 degrees like that, but at 8 meters per second. All right. This one's slightly higher level of difficulty, but it's the same problem. There's some trig involved, a little bit. And I don't want to make these problems all this mathematical. They're really not that many of them, but the look on your face suggests we should look at this one. So please take a moment, break this one up into momentum in the x and y, and break this one up into the momentum in the x and y. Ultimately, what I want is how much impulse was experienced by the ball. So, I mean, we know the momentum, the total momentum before and after. Now, to deal with the triangle portion here, you just got to pick one of the angles that works for the way in which you've drawn your triangle. If this is 60 degrees, then this must be 30 degrees. It's going to use the 30 degrees that's there. This is the adjacent side, so it must be the cosine function. That's going to make that 40 times cosine 30 degrees. That must mean that this is 40 sine 30 degrees. And at this point, I don't have to draw out a whole triangle to know that this must be the other component. If I can identify the one that's the first component, then the other one has to be the opposite sign, the opposite trig function. Any questions about where either of those things came from? I'm going to do the same thing on the other side. I'm going to recognize that this is 30 degrees. It has to be. So this is going to have to be 32 cosine 30 degrees. And this one's going to have to be 32 sine 30 degrees. I'm just doing the trig and trying to break up the momentum into its x portion and its y portion. I'm seeing some confused faces, but are there any questions about this?
Could you look at it like the other way? Like, put the y on the other side and say it was 32 sine 30?
Yes. I mean,
Same thing.
let me be careful here. This component is either the sine of 30 or the cosine of 60. Okay, as long as we're okay. Right, that's fine then. So when I look at this, it seems to me that both components changed. Now, yeah, you should take a moment, grab that calculator, and figure out how much each of these things is, doing your trig. But I'm going to just go forwards here and say that there's the change in momentum in the x direction and the change in momentum in the y direction. I need an agreed upon direction to call positive for both of these. So I'm not going to change anything. That's positive in both directions for me. So it looks to me like the final momentum in the x direction is 32 sine 30. That's this momentum. Minus the initial momentum in the x direction, which was 40 sine 30. That's got to be the change in momentum in the x direction. Any question about that? All right, so I'm going to keep going with that. So move it up a little bit higher because people are struggling to see. So in the y direction, I'm noticing that it's going down initially and then up after the collision. So the final momentum is positive 32 cosine 30. minus the initial momentum, which was negative 40 cosine 30. Now, I know you guys have your calculators, so I know you guys can blow through that and get me a number. So take a moment, make sure you get a number for me, because I want to talk about the results of this. So I'm just going to call out a couple of you. You guys probably tell me what the answers are. Do you need a minute before I call you out? Joseph, can you give me one of them? -4. This seems very reasonable. And Trevor, do you know the other one? It seems very, very likely. You said 62.3?
Yeah.
I think it was just 20 and 16.
That was the X direction.
Oh, that was extra. So, all right. So 62.3 kilograms meters per second. Now, this part might not be obvious to you, so I want you to kind of hear me out. This is how much the Y momentum changed. And it should, notice how big it is. It was going down. We had to stop it from going down, change its direction, and make it go upwards. That's why there's a big change in momentum in the Y direction. It's positive because it had a negative momentum, which we had to absorb, turn it around, and push it back. But in the X direction, there's a negative change in momentum. Well, the object was traveling to the right in the X direction, and it's still traveling to the right, just not as fast. So something had to push on it a little bit to the left. That means that in the course of this collision with the wall must have pushed on it with a force that was like that direction, upwards and a little to the left. It's the only way it could have slowed down some, go into the X direction, but change direction in the Y direction. That's the noise of me having to do some contact tracing. I had to make it make a noise because otherwise I wasn't going to pay attention. That means somebody in one of your classes is probably sitting next to you who now is not going to be here for about 5 days. How are they notifying you guys that you're sitting next to the COVID pod? Are you getting something like? They call parents. Okay. The best part is that we're not hearing anything. So, but I will say that. So again, just in case you missed some of the details, Superman's just standing there, and he is bulletproof. So a bullet has been fired at Superman. It's going to bounce off of Superman, and the bullet is 30 grams. That's 0.03 kilograms, and it's traveling at 500 meters per second. It bounces off his chest and recoils right back in the direction it came at 400 meters per second. What is the impulse experienced by the bullet? And before you give me a number, be careful of what you're about to tell me. I should just pick on somebody. So, I don't know. Who should I pick on? Edward, let's pick on you. What'd you get? Negative what? Anybody back him up? Nobody has your back. Not one person raised their hand. One person raised their hand. 2 people raised. 3 people raised their hand. All right, I'm going to assume you're right. What'd you do? Perfect. Everything done exceptionally well. The only thing I would add to it is make sure that we state from the beginning that our direction was positive, was to the right. That way our impulse was negative, because the bullet was stopped and turned back around to the left. So that looks great. Good job. Now, that being the impulse experienced by the bullet, let me ask a simple question. How long did the bullet touch Superman? We have an answer, right? 0.1 seconds. How long did Superman touch the bullet? Is there any chance he could touch the bullet for a longer period of time than the bullet could touch him? So we're in agreement that that has to be true, that the bullet was in contact with Superman while Superman was in contact with the bullet. Now, if you don't know where I'm going with this, Newton's third law states that for every force, there's an equal and opposite reactive force. That's what Newton's third law states. So if the bullet pushed on Superman, then Superman pushed on the bullet. And those have to be equal and opposite forces. That's Newton's third law. Everybody follow along? That means there must be equal and opposite impulses. Has to be. Newton's third law applies to impulse because they have to experience the same force for the same amount of time. So if I asked you for the impulse on Superman from the bullet, well, then that would be positive 27 kilograms meters per second. That had to be the impulse on Superman. So the impulse on the bullet was negative 27. The impulse on Superman had to be positive 27. So if I know that Superman is 90 kilograms, we could find out what his momentum is after the collision, how much he recoils due to the bullet bouncing off of him. Anybody shot a gun before? You understand recoil then. Recoil is this effect. The gun pushes on the bullet, and therefore the bullet pushes on the gun. If you're holding the gun pushes on you. There's more than enough videos on YouTube of people not knowing that and getting clocked in the head by their own gun. So if you want some funny times, YouTube is full of things to laugh at. Now, this is going to lead to something we're going to do tomorrow. So I want you to understand, right now, if I ask you to calculate the force on Superman, you should be able to do so because you can calculate the force on the bullet. We know the force on a bullet comes from the impulse we already calculated. So if the bullet experiences negative 270 newtons, which is how much force you will get here, then Superman experienced positive 270 newtons. Newton's third law. Tomorrow we're going to talk about collisions. And collisions are a matter of impulse. We're going to do an activity. It's not really a lab, but it's an activity. So I got the tracks back, so we'll be able to do this activity tomorrow. The activity will take about half the class period. We'll have a discussion for about half the class period. You will be taking data, and what you will collect tomorrow will be turned into a laboratory-like assignment that you will turn in. Okay? Any questions? That's it for today.